Screwdrivers. Invented centuries ago, they have become a common item in daily life that is found and used everywhere, from basic home utilities and appliances to major production factories. But what makes a good screwdriver? Is it the ability to turn a screw? What about its features? In this presentation, the main focus will be on a common variation of the screwdriver, the multi-bit screwdriver. This screwdriver features bits that are swappable for screw type and size to make it as universal as possible. Its size also allows usage with smaller screws, such as those seen in cell phones. Screwdrivers are used everywhere, which means they're exposed to tons of different environments. This means the screwdriver has to be able to withstand these environments, or else the screwdriver will become more susceptible to failure. Corrosion, specifically, is a huge consideration since screwdrivers can face exposure to heat, water, and chemicals during usage. In order to produce the ideal screwdriver, many things must be considered in its design. Corrosion is a huge factor to consider during the overall lifespan of the product, likewise with magnetism, toughness, and durability. On the screwdriver's bits, there are signs of corrosion primarily around the point where the bit connects to the screwdriver housing. Due to this connection point, pitting corrosion can be caused by the hexagonal housing interacting with the upper portion of the bit. The contact between the bit and the housing inherently causes scratches and pits to form. Prevention of this requires different material choices, in which better material choices are the most feasible option to reduce the amount of damage caused by the constant forces to the metal surface. Materials resistant to this damage are ideal in this particular case. Moisture in the air, sweat, water, or exposure to chemicals are the factors causing galvanic corrosion. Water is a good electrolyte, and it tends to combine with carbon dioxide in the air to form a weak carbonic acid, which is a better electrolyte. As the acid is formed from moisture in the air, water is broken down into hydrogen and oxygen. As oxygen combines with the metal, the electrons liberated from the anode portion flows to the cathode, causing galvanic corrosion. Corrosion increases with increasing sweat rates, assuming an increase in sodium chloride concentration on the skin surface due to the evaporation of water. The presence of the chloride will facilitate galvanic action between the steel and the sweat. Protective methods are hand washing, keeping the screwdriver bits dry, and avoiding exposure to chemicals as their presence speeds up the corrosion process. Traditional screwdrivers are usually a single piece, in which the handle of the screwdriver is mated to the shank and its blade. Multi-bit screwdrivers typically make use of magnetism by breaking the shank into two parts, one part mated to the handle with a permanent magnet and another part with the blade. This magnetism is essential to the construction of this screwdriver. Of course, this magnetism comes at a cost. The attachment mechanism now introduces another contact point between the shank parts. Now, toughness must be considered between the outer part of the bit and the inner part of the shank. Tough materials are required to prevent scratching and deformation as torque is applied to the screwdriver. Softer materials will not only deform the material, but also introduce scratches and make the screwdriver bit more susceptible to pitting corrosion. The screwdriver in question is made for smaller screws, thus having very thin screw bits. This means the inherently small nature of this product will drastically reduce the amount of torque required for failure. All of this is required to maximize the durability of the screwdriver. The main constraining factor in designing this screwdriver is its price. Sure, these screwdrivers made to withstand industrial loads exist, such as those with diamond or gold coatings. Those may be suitable for use with impact guns and the like, which exert forces beyond human capability. But in this case, the main focus is mass production for the general population. The price limit for the new design is $10 Canadian, which is approximately 1.5 times the price of the current model. The main price factor in the new design is the material. The volume of all the bits is about 2.5 centimeters cubed. This small form factor should be maintained in a new design, therefore the volume is restricted. Because of this small volume, weight isn't too much of a factor, since most materials would produce suitable weights. Even gold would produce a total mass of about 50 grams, which is still reasonable. Finally, the machinability is another factor to consider. The screwdriver's small bits have to be reproducible without too much difficulty to reduce production costs.
In order to select the proper material out of thousands of other options, the Material Performance Index (MPI) can be used to limit material options in the material selection process. MPI is derived by accounting for the constraints and material properties in both the objective and functional requirements. In this particular project, we try to determine a better material for a small handheld screwdriver drive bits while minimizing the material cost. This eventually leads to the objective equation. Cost equals cost per volume times volume, where the total cost needs to be minimized. In addition, the functional requirements is to have a drive bit that allows people to turn and drive the screw without plastic deformation. Since the drive bit is operated by applying torque onto it, it can be represented by the equation of torque. Torque equals K times yield strength over diameter, where K equals pi over 2 times radius to the power 4. After finding the objective and the functional requirements, the first step is to determine the free variable in both equations. In this case, the radius r is set to be the free variable, because the drive bit radius can vary from 2 mm to 5 mm depending on the size of the driver. As shown on the screen, the next step is to isolate the free variable r in the functional requirements and substitute it into the objective. By doing this, a more complicated cost equation that accounts for all the set requirements variables is determined and is further rearranged into the following equation. Cost equals pi times length times 4 times t over pi to the power of 2 over 3 times cost per volume over strength to the power of 2 over 3. And this new equation above can be separated into two parts, a constraint constant term c and the material property term m, where c equals length times pi times 4 times t over pi to the power of 2 over 3, and m equals cost per volume over yield strength of to the power of 2 over 3. According to the new equation, m must be minimized, or 1 over m must be maximized to achieve the goal of minimizing cost. In short, the Material Performance Index MPI for this case is derived as yield strength over cost per volume. With the derived MPI, it is important to plot it onto the Ashby diagram. Since the Ashby diagram for the yield strength varies price per unit volume, it is plotted in the logarithmic scale. A logarithmic function needs to be applied to the MPI term as shown. Eventually, a linear line for the logarithmic plot is derived, with a slope of 1.5. Moreover, the point that the slope passes through is derived by substituting the set variables into the equation. MPI m1 equals yield strength to the power of 2 over 3 over cost per volume equals length times pi times 4 times torque over pi to the power of 2 over 3 divided by cost, where the torque is set to be 0.176 Newton meters, as it is required torque for a 2 mm screw. Length is set to be 8 mm, as it is better to keep the original size. The cost of the part is estimated to be $0.1 based on the purchase of the price. By setting the X value, cost per volume, to be 1000, the Y value, yield strength, can be derived as 0.0008929, making the linear line with the slope of 1.5 through the calculated points. More importantly, the MPI line limits the material selection to around 1200 options from 1800. Other limits and constraints must be applied to get the smaller number of options. An additional horizontal line is plotted onto the diagram based on the calculation of minimum required yield strength. This equation specifically accounts for the minimum radius of the drive bits to determine the minimum yield strength that is required. In this case, the minimum yield strength is 224.1 megapascal. In addition, the property of magnetism is also applied as the limit, as it is part of the functional requirements, as well as the corrosion resistance. The pitting resistance equivalent number PREN from 25 to 50 is applied for a medium to high pitting corrosion resistance. In the end, the material options are limited down to 38 only. After applying the MPIs to the material selection, the material that fit best are tool steel and stainless steel. Cast iron was also on the list, although it lacks in terms of machinability. Between tool steel and stainless steel, there are benefits to each. Tool steel has better resistance to pitting corrosion with a pitting resistance equivalent number, PREN, of 33.8, and stainless steel, on the other hand, has the PREN value of 31. But is significantly cheaper than tool steel at 1.69 US per kilogram in comparison to 8.11 US per kilogram for tool steel. Because of the significant cost saving with a slight sacrifice of corrosion resistance, stainless steel is the new choice of material. The type of stainless steel that is chosen is the AISI 446 stainless steel.
It possesses a ferrite microstructure, which is a body-centered cubic crystal structure containing high percentage of chromium. Ferritic stainless steel is systematically similar to martensitic stainless steel. For this reason, no heat treatment other than annealing is possible for strengthening due to the chromium content. It can be strengthened by cold work, but not to the same degree as austenitic stainless steel. Although work hardening works for ferritic stainless steel, it is hardened by the least out of all three types of stainless steel. The ferritic alloys, particularly AISI type 446 steel with its high chromium content, have desirable properties of corrosion resistance. Added chromium and molybdenum content results in even higher corrosion and oxidation resistance, and is best suited for areas of high corrosion. The application of a paint coating is a cost-effective way of preventing corrosion. Paint coatings act as a barrier to prevent the transfer of electrochemical charge from the corrosive solution to the metal underneath. By taking measures to control the environment, corrosions can be minimized. This can be as simple as reducing exposure to rain or seawater, or more complex measures such as controlling the amounts of sulfur, chlorine, or oxygen in the surrounding environment.
Even though the screwdriver has been around for centuries, we still manage to improve it. New materials and new mechanisms continue to be produced. Even the oldest of tools can be improved. The screwdriver, the most basic tool, a timelessly essential addition to the toolbox.